Hello everyone and welcome back to International Webinar Series Chapter 2 hosted by GeoVigyan. Before I start, I would like to tell you some things that I always tell, that during the lecture you will be shared attendance and feedback form in the YouTube chat live box. There you can fill those forms and you can ask your questions in YouTube chat live and we will take your question directly from there. So coming to today's webinar, today we have with us Dr. Priyadarshi Chinmoy Kumar, who is currently working as a scientist at Wadia Institute of Himalayan Geology, Dehradun, India. He received his MSc Tech in Geophysics with first class distinction from the Department of Geophysics, Andhra University, Visakhapatnam, and in PhD in Science Geophysics from Andhra Academy of Scientific and Innovative Research, CSIR, and GRI, Hyderabad. In 2019, he worked for a short while as a research associate under the mentorship of Dr. Kalachan Sen at Wadia Institute of Himalayan Geology. His research interest includes processing and interpretation of seismic data, design and development of workflows for computation of meta-attributes, seismic structure, and stratigraphic interpretation and sedimentary basin studies. He has authored and co-authored a number of research papers published in peer-reviewed and high-impact journals of repute. Recently, he has co-authored a book entitled Meta-Attributes in Seismic Interpretation, Theory and Practice, published by American Geophysical Union, John Wiley and Sons. He has been recognized with Professor R.C. Misra Gold Medal 2019 by Wadia Institute of Himalayan Geology, Dehradun, and Dr. J.G. Negi Young Scientist Award 2019 by IGU, Hyderabad. One of his papers has received the most downloadable recognition by Elsewhere. His research has attracted both the industry and academia. And today he is with us to enlighten with his knowledge on the topic seismic interpretation, a peep into the subsurface. So, over to you, sir.
Okay, thank you, Subham, for your introduction, and I welcome you all for spending your valuable time for my presentation to listen to me. I am, as Subham said, I'm Dr. Priyadarshi Chinmoy Kumar. I work as a scientist in Seismic Interpretation Laboratory of Wadia Institute of Himalayan Geology, Dehradun. And before I begin my presentation, I wish you all a happy stay safe, and stay healthy, stay with your parents, stay with your family, and also take protection, stay away from this pandemic. And I wish all my hearty wishes to listeners from the country India, as well as also from those who have joined for today's webinar abroad. Okay, so good evening to all of you. Well, today's my lecture will be something interesting on seismic interpretation, how to interpret seismic data, and how to look what you are having within your subsurface, how to interpret the subsurface, and how to look around the geology that is hidden within the subsurface. I will make sure that I will not make you bore out of my presentation, and don't worry, not much mathematics is involved within my presentation. Rather, I have some good images within the slides. I think that will entertain you and keep your interest continue towards the end of my lecture. Okay, so today's contents are something like this. How to peep into the subsurface. Then I will talk about interpret the subsurface, the motivation behind interpreting the subsurface, how are we motivated to interpret the subsurface, how we shall look into the subsurface, and what geological information that we can bring out of the subsurface. Once we have we are motivated towards this, we will look how we can use reflection seismic data for interpretation and what are several techniques that are involved in interpreting reflection seismic data. Then I will take you through a recent case study that I and my team has done over a basin in offshore New Zealand, and I will show you some images, how we try to do geological interpretation out of those images. Then I will shed light on the most fundamental and the most important topic of the day, that is called as machine learning, how machine learning is used for seismic interpretation. And I will also show that how we have done some of the case studies using machine learning techniques for interpreting seismic data. And finally, I will talk about something called as our laboratory, Seismic Interpretation Laboratory, that we have established at Wadia Institute of Himalayan Geology. And of course, we require lots of students, lots of doctoral students, lots of postdoctoral students who can collaborate with us and give seismic solutions to industry, and also try to bridge the gap between industry and academia. Finally, I will give you a takeaway message from my presentation. So here is something I try to bring some images from Google. Now the fundamental question is that when I show you that how to peep into the subsurface, you must be thinking that how shall we do it, how to look into the subsurface. The simple answer is by taking the help of a technique which is called as geophysics, and by performing some geophysical experiments. Like here you see we have this image shows some seismic experiments they have performed. Here this image shows some electrical resistivity experiments they have performed. And these are the several geophysical experiments that generally are done to image the subsurface, to get information what is hidden within the subsurface. And finally, you analyze this image, and from this image, you try to speak what is the geology within the subsurface. So what is the motivation? Why should we interpret the subsurface? Some image, I have again taken it from Google, and you can see that something you have here, some good colors. You have some maroon colors here, you have some green colors here, then you have some red colors here, and you have some blue colors here. And you see some lineament like some curve-like features. So all these things create a curiosity that what exactly are these? What exactly are these? How these are prepared? And from this, you try to understand that is the subsurface geologically complex? How does this subsurface looks like? Or you can see here the image that I have shown you, that how the subsurface layers are structured. Can we identify some geological resources for exploration and exploitation? So all these questions gives curiosity, makes you very motivated to use the seismic technique to peep into the subsurface. This is something called an image that I have shown you. And generally, how does reflection seismic data? Reflection seismic is used for looking into the subsurface. At the end of the day, you see some receivers and some recording instruments are present in the surface. Then the seismic waves try to penetrate into the subsurface, and finally, when it comes into the receivers here, we process the data and we prepare some images like it is shown here. Now, when I see this image is nothing but a photocopy of my subsurface. Now I try to understand what are these layers, what is this black represent, what does this blue represent, and what does this red represent. So that is called as interpreting the image that will result into a geological story, how my subsurface is structured or how my subsurface looks like. And mapping the subsurface is the fundamental principle of seismic, which is widely used in the oil industry. Like, for example, if you see to this image, you can see something. If you being a geologist try to think that how the subsurface looks, then you immediately say, oh my god, I see something called some folded like structures. Oh, something is happening here, some reflector, or maybe some faults I see here. I see some folded beds here. So all this, when you try to say, this is what you look into the subsurface, or you peep into the subsurface, and from what you peep into the subsurface, you use the seismic as the image. You use the seismic image to peep into the subsurface. So that is called as peeping into the subsurface by looking into the seismic image or by interpreting into the seismic image. Generally, how you interpret or how you look into the seismic image, there are two fundamental aspects in which you can look into the seismic image. Either you can see the image in a cross-section view, that is crossing. Suppose if this is the surface and I try to cross it, I try to make the slice vertically, then I try to get a cross-section. So from this cross-section, I try to interpret some geology. I try to look at the image. I try to look at the subsurface from this cross-section. And when I try to interpret this image, so this is called as cross-section interpretation. Now, if you look at this image, you see something called as a surfacial image, or what we call as map. So when you try to interpret a map of the subsurface, like for example, if you see this particular layer at this position, and you try to slice this layer, then you get something called as this. Like for example, when you go to the market, you purchase the box of bread, and you try to slice out of the bread horizontally. Something, you get the image like this. Now you try to interpret this image. You try to add some geological information from this image. So that is called as interpretation of the subsurface through maps. So several interpretation techniques are generally developed, and which has developed from since the past decade. And geophysicists, geologists use these interpretation techniques to achieve their objectives. Now, what are those interpretation techniques? Those interpretation techniques are always defined by your objective, what objective you have. For example, if you try to interpret some structures, like for example, here you see if this is the subsurface image, then you see some beds are going up, some beds are going down. So what you try to make it out of geology, you say that here you have some host-like feature, here you have some gravel-like feature. So when you try to interpret these structures, then those type of interpretation are called as structural interpretation. You try to interpret some structures out of your data, out of your subsurface data. Now, when you try to interpret some depositional patterns, like for example, you see, if you have some beds running parallel like this, if you have some beds running sigmoidal like this, then you try to understand that how this thing has been deposited, what was the depositional pattern of this bed, then such type of interpretation is called a stratigraphic interpretation. Now, if you try to understand how some sedimentary features within the subsurface behaves, like for example, I showed here some channel-like features, and you try to understand their orogeny, how did they form, what are the geomorphological complications are involved within those features, then those type of interpretation are generally called as geomorphic interpretation, or in the terms of seismic, we call as seismic geomorphology. Again, here I show some of the image related to some recurrent mass activities. Now, as a sediment, as a sedimentologist, or students from sediments, sedimentary geology, they try to understand what sedimentary flow of the subsurface has taken place. Now, when you try to understand those type of features from the subsurface, then those are related to sedimentary interpretation, sedimentary information. You are revealing all sorts of sedimentary information from the image. You're trying to reveal all type of geomorphological interpretation from the image. Like for example, as I have shown here, these are if given this image to me, I will be very interested to look at how the sedimentary features behave. What are several geological structural complexities involved within the sedimentary features? How are they arranged, and how have they evolved with time? Then when I try to interpret through several maps like this, then those are called as interpreting those sedimentary features or those geomorphic features from map. And if I try to interpret them from cross section, then I try to interpret using several cross sections, and I try to identify each of the image, that is each of these images, each of these layers, what geology does these layers speak from this image. So such type of so all this what I now explained to you are several interpretation techniques or interpretation approach which generally geologists or geophysicists undertake in order to make out more from the subsurface. I mean to say, in order to interpret the subsurface from the seismic data, they try to utilize all these techniques, and they try to interpret the subsurface so that much information, much geological information could be brought into picture. Okay, so now let us try to learn through some case study example that how really this interpretation is done and how we try to interpret our subsurface. This case study example, I will talk with you, I will share with you my experiences. Excuse me. I will talk with you my experiences that I and my team have carried out in this year, understanding how magmatic intrusions, what are the consequences of magmatic intrusions, or when a magmatic body try to intrude into the host, what type of consequences they develop. Especially they develop a beautiful scenario which we call as forced fold. So what are those forced fold, and how can we interpret from the subsurface? This is a beautiful example that I present to you from a very well-known petroliferous basin which is present in offshore New Zealand and is called as Taranaki Basin. And I request all students and all of my, the listeners, you can all download this paper, and you can read them. You can understand all geological complexities which is involved within this particular case study research. So what is called as forced folding? How do we define these forced folds? Generally, I assume that all of you know, all of you have a glimpse of knowledge regarding magmatic seals. I mean, we define it in terms of seismic. We define it something called as a Subsurface structure having a layered parallel intrusion where you have your limbs rising towards the limbs keeps on rising towards up and up, allowing the magma to flow into the host environment. Now, when this particular feature tries to grow, giving it to a Subsurface structure, then the overburden host tries to accommodate this type of structure, and when the host tries to accommodate this type of structure, then a type of structural complexities tries to grow, or the bed become folded, which is generally termed as forced fold. This was for the first time investigated in the year 1978 by Stearns, who defines this forced fold as folding in which the final overall shape and trend of the fold are dominated by the shape of the forcing member. You have a forcing member. This is the forcing member. Now, this forcing member tries to enter into the overlying strata and tries to fold the strata. So this forcing member is forcing the overlying bed and trying to fold the overlying bed, which we call as something forcing the overlying bed and making the fold, which is called as forced fold. Now, how these forced folds are important? Forced folds are well-known structural traps. If we talk regarding hydrocarbon resources, then for an explorationist or for a geologist, when he looks at forced folds, he says, my day is done. because that's a beautiful structural trap which engulfs a huge potential for hydrocarbon resources. Now, what are the occurrence and distribution of this type of structure? Some of the noted examples where this type of structure have proven to be have good hydrocarbon prospects are some basins from Thailand, Senegal. You can see from offshore Norway, Argentina, Northwest Australia, Southern Australia, offshore Northeast Ireland, Northeast Atlantic, and WIHG Bui Basin again from Thailand. In Taranaki, our objectives were to understand the structures and geometry of the force fold that were developed above selected magmatic seams in the study area, and to understand if the dimension of the force folds are directly related to the volume of intruded magma below, or instead there is any discrepancies in folds in relationship. And finally, once we understand the point number 1 and point number 2, we try to frame out a conceptual model how this development of force fold has taken place. Again, I repeat, all things are done using reflection seismic data and how we interpret the reflection seismic data to achieve these objectives. This is the basin that I'm talking about, which is this is covered by a set of buried stratovolcanoes, and here we have a very well-known prospect, which is a well-known prospect which is called as the Kora prospect. This prospect was very well known for the buried stratovolcano, which is called as the Kora volcano. And when offshore oil companies tried to drill through this volcano, they encountered a huge amount of oil. If I'm not wrong, something, if I correctly remember, 1605 BOPD barrels of oil per day. There was continuous production for about 10 days. So we had picked up this area to study this beautiful phenomena. And the Taranaki Basin of New Zealand has a complex tectonic environment. It has undergone a multiple phase of deformation that has given rise to different structural and stratigraphic features in the basin. The northern part of the basin, is mainly prone to magmatic intrusions and is surrounded by a chain of buried stratovolcanoes. Yeah, so now what you see something called as the image. What I explained you earlier, you see the subsurface, you see the image in a cross-section view. Now this image is an uninterpreted image. Once it comes in your desk, you try to interpret this image. Now when you try to interpret this image, you try to see several reflections, the pattern of the reflections. And when you look at the pattern of the reflections, you try to correlate this pattern of the reflections to a particular geologic event or a particular geologic feature. So for example, like here, I have shown that for Kora, within the Kora prospect, when we try to analyze this this image, we see the volcano, the Kora volcano that we are talking about is this, which is called as the volcanic formation. And on the flanks of this volcano, we had several onlaps. And when the volcano activity ceased, there was instability within the sea floor. I mean, this was around towards the end of the Miocene. This was towards the end of the Miocene, and towards the end of the Miocene, the volcanic event started to cease out. And after the Miocene, towards the Pliocene and the recent, there was huge sedimentation within the basin. And probably at this position, where I see a lot of chaotic disturbances, which we generally define as mass transport deposits, which means that the seafloor at that position, at that period of time, was very, very unstable, and that led to deposition of this type of recurrent mass events. Now, if we keep on going deep into deep, then we try to see the beds are still getting folded, and again deep, we see several beautiful magmatic seals that have tried to intrude into the subsurface, and they have tried to create this type of deformation. Now, when we see towards the Upper Cretaceous and the Eocene, we see such type of folds are very, very prominent. So our objective was to understand what geological consequences of this force fold occurs between a depth of 4 kilometers to approximately 7 kilometers in the subsurface. Now, analyzing this particular image and try to see these features and try to correlate with the geological significance of these features, we try to analyze each and every aspect of this feature. Like, for example, you can see here, these are the marked silts. First of all, we try to understand that which horizon or which geological strata we are trying to interpret. And once we have marked that geological strata, we try to look into the zone below that strata, and we try to identify these type of geological features, which are called as magmatic silts. Now, once we have identified this type of geological features, we try to understand what are the structural geometry of this feature, what are the structural architecture of these features. Like, for example, you see this magmatic silt have got several type of structures. You see the Sasa base, you see the limbs rising, you see the limbs rising up, you see there are some, the magmatic silts are arranged in several step pattern, going one down the other. So this, such type of interpretation we again bring out from the subsurface, and this type of interpretation correlating with the geology gives lots of information about the geology of the subsurface. Going to the next slide, again we try to interpret some of the magmatic silts and try to understand the structures, that how this type of features have developed, and what type of geological architecture of these structures are. Like, for example, you see some features which are called as broken bridge of this structure, and you see some magmatic lobes. When this bridge got broken, then we call these as individual lobes, and how the lobes are arranged, what are the different arrangement of these lobes, different structure of these lobes. Now, once we have convinced with the interpretation of these forcing members, so these magmatic silts are called as forcing members, we try to make some type of detailed interpretation into these structures. Now, when we try to do some detailed interpretation into these structures, we see that we did some interpretation to these broken bridge structures. Now, these broken bridge structures, you can see the seismic cross sections of these broken bridge structures as they look like here. Now, again, we try to interpret these cross sections of these broken bridge structures. We see that they are arranged in a step pattern. They're arranged in a step pattern, and they have something called as broken bridge bands, and this band starts to deform. Now, how these magmatic silts are related to the force fold development. Now, in order to relate those the relation of these magmatic silts into the force fold, we try to again interpret, after interpreting this magmatic silt, we try to interpret these folded structures. Now, when we try to interpret this folded structure, we see that these folded structures are structured. These folded beds are structured. We see several faulted features. These we see several onlaps, and also we see here. You see when there was no, no development of there was no development of the fold. Then we see these type of structures are trying to penetrate into the subsurface and trying to create several type of disturbances or folded strata. Now, once we have once we are done with this, we try to again understand how the folds are architecture. For example, we see here fold A, fold B, and we can see several magmatic fluids that try to percolate through these magmatic features into the folded structures, and how this type of arrangement in the subsurface has been made. Once we are convinced with all those things, we try to understand the fold morphometry. that how the fold morphometry pattern and what are the morphological significance of the fold is there, and how the folds structural arrangement of these folds are present. So in order to understand the structural complexities of this fold, we try to measure the fold amplitude. We try to measure measure what impact these seals have got over the structural complexities, and from there we try to analyze the structure and geometry of the fold and the area coverage of the fold, and we try to understand that what are the morphometrical details of this folded structure. Like for example, fold A and fold B. Here we see that the crest is semicircular in geometry. The limbs are widened, and if you see to the fold B, then the crest is semicircular geometry showing anticlinal, synclinal structures. Limbs are gently widened, and you can see the cross-section profile shows a stepped or ladder geometry. Stepped or ladder geometry, you can see it easily here. Now, once we are done with all this interpretation, we try to do some type of morphometric analysis of these folds with respect to the thickness of the seal. Now, when we try to compute the morphometric property of the fold with respect to thickness, then we see that the thickness of the seal and the fold morphometry are very positively correlated to each other. After being satisfied with this step, we try to figure out that what is the relation between the intrusion of seals of this folded structure with respect to the length to versus depth of intrusion, because that will give us an idea that which are those seals which have maximum effect of this fold over this folded structure, and which are the seals that have minimum effect over this folded structure. So understanding the fold amplitude versus seal thickness, that is called as L by D ratio, will help us to decipher that what are the geological interrelations or geological implications of these folded structures with respect to the forcing member of the magmatic seals occurs. Now, once we are done with it, we try to understand the seal fold dimension measurements. You see, if we look at the seal fold dimension measurements, we again from seismic data, again from reflection seismic data, based on the seal fold dimension measurements, we try to understand that what type of structural geometry or what type of structural implications of the seal and the fold have with each other, and what are the interrelation exists between them. But if you look at the dimension of the seals, if you look at the length and width as I have noted it here, and if you look at the area as I have noted it here, you see one interesting fact that we observed, that the length to the width, but here we observe the area of the fold to be more with respect to this aspect ratio and with respect to this area. Why does it happen? That was a striking point into our analysis. So from that, we understood that not only the magmatic seals that are able to create such type of structural discrepancies, but there may be some huge magmatic source that was also responsible for creating these large folds. So this was a unique conclusion for which we brought by interpreting our subsurface stratigraphy, that not only these magmatic seals are responsible for creating these gigantic folds, but there is some huge magmatic source beneath, somewhere beneath, that is also having an implications in generating such type of structural complexities. So from this, we understood that this area is not only geothermally very active, but also with respect to hydrocarbon prospect of view, this area is very prolific. This was a very, very new insight that we brought out by looking into the reflection seismic data and by peeping into the subsurface. Finally, we try to draw a conceptual model, and we try to observe that such type of phenomena when happens, the length to the depth ratio of the seal plays a maximum role in formulating these type of folded structures, and all this conceptual model again has been run by looking into the reflection seismic image, or by interpreting the seismic data, or by peeping into the subsurface. Now, the main conclusion of this case study was that the Subsurface seal in the in the Kora volcanic complex resulted in the growth and development of fold within the Upper Cretaceous to the Paleocene strata. The strata are significantly older than intervals in which folds were previously identified. Literature within the Kora volcanic complex. Again, we found that the ratio of seal length to intrusion depth should range from 2 to 6, and in some of our studies recently now we are observing that in some basins this factor can also exceed, and at that position some other geological composition also comes into picture, which tries to create such gigantic folds in the subsurface. Now, our work indicates that large force folds are observed, but only a few relatively small seals are imaged below. The mass of igneous rocks generating such folds is actually larger than what is imaged in the seismic data. Thus, force folds becomes an excellent way to pinpoint the regions which are more magma than expected has intruded into the rock below them. So these type of innovative conclusions you try to bring out when you try to interpret your subsurface, when you try to look into the subsurface and you interpret the seismic data. Okay, so we have done, I have shown you a case study that we have used, where we have used the fundamental seismic interpretation technique in interpreting the seismic data. Now let us make an adventure by learning some advanced topics that is used for interpreting the subsurface, the reflection seismic data, which is called as a very well-known technique called as machine learning, and it is the need of the hour. And you see everywhere the machine learning is nowadays being applied and is a very hot topic nowadays. And in seismic, especially, machine learning has grown at an alarming rate. The application of machine learning has grown at an alarming rate. And I must say that in India, we and our team have performed several case study applications of machine learning using seismic reflection seismic, and we have designed several new what we call as attributes or several new meta attributes that are very, very useful for seismic data interpretation. Now, what is the motivation behind using this machine learning, or what we call as artificial intelligence? Assume that you all are standing in a crowded place. Okay, you all so here are some of your colleagues standing here, and suddenly you asked your colleague, "Oh my God, there is a beautiful girl standing next to me." Then your colleague asked, what made you to understand that girl is so beautiful that out of the entire crowded place, you see this beautiful girl? You suddenly say, "Oh, she is beautiful. She is having a mole on her cheek. She is very white. Her eyes are beautiful." So can you please understand what exactly are you saying? You are trying to understand the qualitative nature of your interpretation. Human brain is qualitatively very, very robust. Human brain is qualitatively very, very active. But if you ask your friend to count each and every member of this crowd, what are their age, what is their identification number, how many of them are boys, how many of them are girls, how many of them are women, and how many of them are very old aged persons, you get perturbed. So when the numerical computation comes into picture, your mind starts to question a lot. At that point, if you write a program or if a computer comes into your picture and you try to enter everybody, the details of everybody who are present in the crowd systematically, you get, you say, oh my God, my job is done. I have done my job. I have every information stored in the memory of the computer. That's what is the motivation behind using machine learning or artificial intelligence. You try to make an interaction with your own neural system to the neural system of the computer, and you try to interact both of and you and the computer, your brain and the brain of the machine, try to interact with each other and give out an optimum solution. So that is what we call as artificial intelligence or machine learning, and it has been very proved to be a robust technique in interpreting subsurface resources. Now, what are called as seismic meta attributes? In seismic method, in generally reflection seismic attributes are very useful, and they are generally most often and very widely used by people from petroleum exploration, and these techniques poses wider application in interpreting subsurface geologic features like faults, fractures, folds, channels, diapers, reefs, and contributes to act. And these features generally contributes to act as potential hydrocarbon traps. Now, when I say seismic attributes refers to seismic properties of that particular feature. Now, when you try to amalgamate that particular properties, you get something called as meta attribute. I will not talk much on the theory of this meta attribute. You can all look into all these references. These references are very clearly mentioned and gives you an exhaustive theory and concepts of this newly designed technique called as meta attribute, and you can read from all these papers what does this meta attribute do. Now, always remember one point: artificial intelligence or machine learning, those are the need of the day, but it is what you are going to bring out from machine learning, what you are going to interpret from machine learning, how much geology you are interpreting from machine learning. That plays a very important role. And throughout the research that we have been performing, our team has been performing, we try to make more geology than speaking less method out of this a particular geophysical technique. All the listeners and all the viewers to today's presentation, I will say that in this winter you can log into Edu Publication House, and in Edu Publication House you can see in this winter our book is going to be internationally released. This is a unique book of its kind, and it is a handy reference book. For the first time, it has come into the international market, where it can be used by numerous number of research scholars, master students, academicians, and industry professionals. It contains complete theory, illustrations, and a large collection of case studies, where we have given an exhaustive information, theory, equations, mathematical derivations, mathematical equations, and several way how a beginner can use artificial intelligence to compute these new techniques, these new attributes, in order to enhance or augment interpretation. And recently, many oil companies have approached us, and we have shared our ideas through this book, and we both of the authors feel that this will be a very handy reference copy for all of you. Let me show you some of example of AI application for subsurface exploration. This was an application. This was an experiment that we performed to identify gas chimneys from seismic data, and we did some AI technique in order to look into the subsurface, and in order to see that how this gas plume starts to propagate from the source through the reservoir back to the surface. So this was published in 2016 in a very prolific journal, Journal of Natural Gas Science and Engineering. This article was published in the year 2018, and it was declared as the most downloadable article by Journal of Applied Geophysics for the year 2018, where we have where we use artificial intelligence technique to improve the fault type of structures. And we performed here 3 different cases where artificial intelligence was applied, and we try to understand that how the faulted structures or the discontinuous features can be improved when we go from case 1 to case 2 to case 3. You can see when you try to look at this image, I think you will feel that, oh my God, in the top portion I could see something, but in the bottom I am not able to visualize what is going to happen. Again, if you see into the case 2, you see, okay, the signal have improved, but again, these are something messy. But if you see case 3, you see that very sharp, crystal clear visualization of these faulted structures have come out. So these are subsurface fault networks, and this got published in 2018. And this is one of a wonderful technique in which we have designed a meta attribute which we call as themed fault cube, and which has been very, very effective in identifying geologic faults from reflection seismic data. Now, if you see something called as fluid migration, generally we see some image when we try to look at the seismic data, and we try to see some image like this, then we become very happy, and we see that, oh my God, I am getting something good thing. Then these type of pool of features are generally responsible are generally interpreted as fluids which is trying to migrate from the through the subsurface strata and trying to travel through the reservoirs. So now the question was that if we can create a visualization, and if we can create an attribute that could distinctly map these fluids propagating from the subsurface through the reservoirs, can we do it? So that was the motivation in designing this attribute, which is called as fluid cube. And you might be thinking that how you validate these results. We take several geological records, we take several well-logged data, and we try to correlate our observation with these data observations, and we try to finally conclude that this particular features that we are talking about is something related to fluid migration. This is a case study that we performed in offshore Norway, where we try to present the structure of magmatic seal. And I would like to inform you that this has been the cover page of ONGC bulletin, and this work was declared by ONGC GeoPeak to be the outstanding contribution in the field of artificial intelligence for the year 2020. So here you can see how beautifully these magmatic seals have brought out, and how the structural configurations of these magmatic seals has come into picture. This was something where we try to correlate both this fluid cube and the magmatic seals, and we try to showcase that how between the Cretaceous to Eocene strata, this particular geological complexities have developed, and how this has tried to come into picture, where we have tried to image the subsurface magmatic seals and the plumbing systems, and we try to understand that how the geological structure, how these geological structures pump out magmatic fluids into the overlying strata. Here we specifically performed an experiment in the volcanic system. We try to understand the entire upwelling system through the volcano, through the buried volcano, which was present by constructing or designing a meta attribute, and we try to see that how this particular interpretation that we are trying to do in the through the manual process, how it could be automated by using this artificial intelligence technique. This was a recent publication which has drawn attention of several sedimentologists, several people who are working in geology, in geomorphology. It was published in Nature scientific reports, and here we have shown a three-dimensional how this artificial intelligence could bring out the three-dimensional structure of recurrent mass units or recurrent mass flow units when there is a seafloor instability, and how these structural complexities can be brought into picture. This this has now, attracted both ONGC Mumbai offshore as well as also ONGC GeoPeak Dehradun, and they have they are very attracted towards this technique. Well, so now I have presented you many of the research works that our group has been doing, and I have been performing since last couple of years. At Wadia Institute of Himalayan Geology, we have taken a new initiative of establishing Seismic Interpretation Laboratory, which is called as SEAL, which main aims and objective is to collaborate with national and international oil companies for performing cutting-edge research in artificial intelligence, in fundamental geological interpretation, structural interpretation, stratigraphic interpretation, understand basin tectonics, basin evolution. We mainly do 3D seismic interpretation. We try to understand how structures behave, how subsurface structures behave, and how those things can be correlated to the outcrops. And we try to also give solutions to industrial questions, industrial challenges. We have collaborated also with National Data Repository of Director General of Hydrocarbons, so that our students can get direct access to industry-oriented seismic data sets as well as also well-log data sets. And our main motive is to help students, geologists or geophysicists to carry out the doctoral research using industry-oriented data sets. And if you are interested to join us, we will be very happy to take you into our group. And our group is growing under the leadership of Professor Kalachan Sen, who is presently the director of our institute. So finally, the takeaway message from today's presentation is something really, I will say interpreting subsurface is very challenging. It is not only one technique that you have to rely, but you have to integrate several geophysical techniques, and you have to interpret the geology. And what I believe is that your interpretation should speak more geology rather speaking more techniques. The more and more geology you speak, the more and more geological complexities you try to solve, the more and more finer details you try to bring out into the desk. And obviously, I will say seismic helps to bring out all these finer details of the subsurface. So my dear friends, accept this challenge. A reward is waiting for you. And I again say that we are looking for interested and very highly motivated doctoral and postdoctoral students to join us at SEAL WIHG. If you're very motivated towards this, you can write to us. You can email us. We will be very happy to encourage you and to accept your interest. Thank you all listeners from national and international community. Thank you for spending your valuable time, and thank you for giving me an opportunity to spend my research expertise, my experience since last couple of years, what I have been handling. And I especially thank to enter GeoVigyan team for your enthusiastic support that you have rendered to me. Thank you all.
Thank you, sir, for giving us so much knowledge about the topic. And surely many will get motivated for what you have said, that you are encouraging all the research scholars, and I think so many of them will be joining under the same topic.
Thank you.
I believe that.
Yeah, okay. Thank you.
Yes. Sir, we would like to take now some questions.
Yeah, sure.
So the first question is that how can we compare statistical approach and AI approach? That It is to ask that which one is better to use.
Uh, um, uh, as a whole, I will say everything, you see, everything, whether you take statistics, you take AI, at the end of the day, what you're doing some type of predictions, right? So whether you take statistical analysis, you take AI analysis, so both of them are quite a bit compatible with each other. But certainly, I will say AI approach always stands at par with the existing approaches.
Okay, sir. Thank you, sir. Sir, could you suggest some of the softwares and the techniques, AI techniques, which could be useful?
Yeah, a very handsome software which you all can use is Weka software tool and Weka data mining tool. And because Weka data mining tool has got lots and lots of applications with it, you have lots of algorithms, you have lots of, you can do all type of machine learning works. And recently, some of guys at Wadia Institute of Himalayan Geology, they have published paper using the Weka machine learning tool. So that's for doing topics for dealing topics like when you have column-wise or row-wise data. This type of tools Weka machine learning tool is very handsome and very beautiful. Other than if somebody are interested to code themselves or to write some programs, you can go for a Jupyter notebook of Python. You can write some programs in the Python. So that is a good option to use. Or else if many of the students are not well accustomed with the programming language, no need to worry, because Weka tool has a GUI based platform within it, graphic user interface. So you can enjoy step by step by learning all this software.
Yes, thank you, sir. Next question is role. What is the role of well logging in the seismic data interpretation?
Oh, that's a very beautiful question. Yeah, well logging, the role of well logging plays very important in seismic data interpretation, because what happens when you try, now the basic difference why you try to incorporate well into seismic, because when you try to look into the well data directly give you the depth information. The vertical axis is the depth axis, right? When you look at the seismic data, you have the vertical axis and the time axis. So always when you try to interpret the seismic data, you're trying to interpret in a particular time information. But the well you have is a depth information. So when you try to correlate the well with this time information, at the end of the day, you're trying to have a much more effect on your improved interpretation towards the question that you are the objective that you are framing for. So well logs plays a very important role in seismic interpretation.
Thank you, sir. So next question is, can you explain about time structure maps?
Yeah, I have not yet shown. I'm sorry, I haven't shown it in my presentation. Yeah, time structure maps plays a very important role, which we call as from which we try to observe several how the contour patterns, how the contours at the same time, how the contours looks like, and from the time structure map we try to prepare the depth structure map, and from the depth structure map we try to understand the contours patterns and closures, how the contours make, and from the closures or from the contours we try to locate that where are our traps and where which are those areas that contains traps, or which are those areas that does not contain traps. So these so they are generally called as isopac and isochrone maps. So these isochrone and isopac maps plays a very important role in understanding these concepts.
So next question is, can we interpret seismic data in ArcGIS software?
I'm afraid I think ArcGIS software is not compatible for interpreting seismic data, because seismic data generally the format of seismic data is .segY, SEGY. So ArcGIS generally has something called as the extension, some ASCII format or some DAT format. So I'm afraid ArcGIS will not be so, may not be able to take seismic as an input for interpretation.
So next question is, how is seismic method used for determining earthquakes?
Okay, the seismic method for determining earthquakes, that is called a seismology. That is a branch of seismology, and especially the seismology is used for earthquake modeling, earthquake understanding. But my expertise is not in seismology. I am in applied seismology. I'm unable to hear you.
Yeah. So next question is, can exploration of gas hydrates be done by seismic data and interpretation?
Yeah, exploration of gas hydrates can be done by seismic data and interpretation. You can look a numerous number of papers. You can look a numerous number of papers of Professor Kalachi and Sen, where they have shown that seismic data is very, very useful in interpreting gas hydrates.
So next question is there any interlink between diaper and forced fold?
There is no interrelation between diaper and a forced fold, because when you talk about diaper, it is something related to salt tectonics, but forced fold is completely related to emplacement of magmatic bodies.
Next question is, what well logging data is most important for seismic interpretation?
Several logs. I mean, it depends on your objective. What type of objectives you are having? If you are having stratigraphic if you are having an objective for stratigraphic interpretation, then you go for gamma ray logs. If you try to identify some gas pockets or presence of some gas migration or some gas plumes is present in your subsurface, then it's good for understanding for correlating porosity, neutron porosity, and resistivity logs. So based on your objectives, you have to select the logs.
The next question is, what software needed for time structure map making?
It's the general software. I mean, general interpretation suite that is available, but we call as you can go for Petrel's the spectral tool of Schlumberger. You can go for DGBR, Open Detect of DGBR Sciences. You can go for JSON suite of CGG Veritas. So I think these software are good for seismic data interpretation as well as also preparation of structural maps.
Sir, are there any free software available for logging interpretation?
Free software, I don't have an idea.
Sir, going to next question. Based on silt definition, it flows parallel to bed, and how does it force? I doesn't understand the phenomena perfectly, sir.
When the seal when the seal starts to grow when the length of the seal tries to grow and grow, then the limb then it tries to spread out laterally. Now, when it tries to spread out laterally, it tries to the magma tries to move through the lobes and the limbs. Now, when the limbs tries to transgress upwards, then the strata, which is then the host sedimentary strata, tries to accommodate this. This type of structure. So automatically it gets folded.
Coming to next question, how seismic interpretation helps, or what is the role in wireline logging in petroleum exploration?
Wireline logging is used in petroleum exploration. Again, I will say I will put this answer in this way, that all this well logging, well information helps seismic interpretation for correlation.
Okay, thank you, sir. With this, we came to end of our question and answer round.
Okay.
Thank you very much, sir, for enlightening us with the knowledge of seismic interpretation.
Thank you. Thank you all for spending your valuable time to us.
Thank you, sir. We are fortunate to have you today on our talk. Thank you.
Have a nice time. Stay safe. Bye-bye.